Vaibhav Kukreja, and he will talk about stability of transuranic characteristic discontinuities in two-dimensional Euler equation for steady compressible Euler flows.
Okay, thank you. So I would like first to thank the organizers, Professor Linares and Professor Fried, especially Professor Fried for giving me a chance to come to IMPA and present at this important meeting. So I will talk about stability of transonic discontinuities. This is a joint work with my PhD advisor, Professor Guichan Chen and Professor Hirong Yuan from East China Normal University. Okay, so here we start off with conservation laws. U is density and F represent density flux. We'll be looking at steady state solutions, so we drop the time component and look at divergence of F equal to 0. We'll focus on the Euler system for steady compressible flows. Here U is the velocity, P is the pressure, rho is density. The first equation comes from the conservation of mass, the second from the conservation of momentum, and third from energy. E is the internal energy. Entropy is given by the following expression where all the constants are positive here. C is sound speed, and we define the Mach number to be the ratio of the velocity to the sound speed. So we say the fluid is supersonic if the Mach number is greater than 1. Fluid is subsonic if it's less than 1. It's sonic if it is equal to 1. Okay, it is well known that for smooth data for the Cauchy problem, singularities develop in finite time. So we need admissibility criteria to pick out the right solution. So we say a function in BV is an entropy solution to the problem if it is a weak solution satisfying the initial data and the boundary data, and if it satisfies the following entropy inequality in the sense of distributions. And this is again to pick out the physically relevant discontinuous solutions, especially shock waves. Okay, so in earlier talks, particularly by Professor Chen and Professor Serre, there had been much discussion about stability of weak shocks, strong shocks. Particularly in Professor Serre's talk, there was a discussion on the existence of characteristic surfaces in multi-D. But today I'll focus on the 2D steady Euler system. So all the discontinuities will be in the XY plane. So here's the setup of the problem. So we have incoming supersonic flow, a uniform state. It's a straight flow, so the V component is 0. So what happens is we have a supersonic flow coming over. You can consider this as a flat wall. At this corner, this convex corner, there emerges a transonic characteristic discontinuity. So this is a vortex sheet, either or an entropy wave or a combination of the of both. So here what we have, the reason it appears is because you have still gas. So supersonic flow comes in, below the x-axis we have still gas, and we have this strong discontinuity emerging from this convex corner. So we set up the following initial boundary value problem. Here the two critical boundary conditions are that across this discontinuity the pressure is the same as P bar, and the flow satisfies the slippery boundary condition along this characteristic. So the question we're interested in whether such a transonic discontinuity is structurally stable if you add small perturbation to the initial data at x equals 0, or small perturbation to the upstream supersonic flow. Okay, I want to say a little bit about instability and stability of unsteady vortex sheets. So what are vortex sheets? Vortex sheets are surfaces across which the tangential velocity jumps sharply. In our analysis, there are also entropy waves. These are waves across which the density jumps sharply. So there has been various different analyses indicating stability and instability for Mach number greater than square root of 2 or less than square root of 2. I'd just like to point out what this means for our results. So what we have been able to show is that steady supersonic subsonic vortex sheet as time asymptotics are stable in structure globally, in contrast to the prediction of instability of vortex sheet at high Mach number as time evolves. So this is what these numerical simulations, in very important work done by Artola, Maeda, Woodward, indicated that you see that vortex sheets become unstable for Mach number greater than 2. So here is another example of instability. This is the Kelvin-Helmholtz instability, and this instability arises as these waves that are propagating along. Now, these are truly multi-D phenomena, so currently they're not much known about the right solution spaces to study these things. Okay, so why should we study steady flows? Well, steady flows, they're asymptotic states and maybe global attractors for the corresponding unsteady Euler flows. So this sheds much light on the long time asymptotic behavior of unsteady flows. Here I mentioned a few important references related to this. The Courant and Friedrich book has many important steady problems. These are some additional papers looking at stability of vortex sheets and strong shocks and in steady flow. Again, these references also have a lot more information about the physical and the numerical experiments looking at the instabilities of unsteady compressible vortex sheets. Also, there have been work done for general systems in 1D. So the first one deals with contact discontinuities. Here's another paper that deals with the stability of strong shocks for general n-by-n systems. So here I mentioned some further references on the method of wavefront tracking. This method is what we use to tackle our problem. There are various versions of this method available, particularly the two favorites, or the really favorite is the one by Professor Bresson. There's also one by the Norwegian school by Professor Holgen and Resborough, and this is the method we adopt to tackle our problem. Also, I mentioned here this very seminal paper on interval stability for n-by-n systems in 1D, and many of the tools for the L1 stability analysis I will talk about come from this very important paper. Okay, so what are some key issues, new features from our work? Well, so far in steady flows, there have been several works where vortex sheets and shocks have been studied with just supersonic flow, or there have been work with subsonic flow. But with mixed type flow, there's always this assumption that the supersonic flow is continuous. So there are not so many work with transonic discontinuity where the supersonic flow is not C1 and belongs to the BV space. So some of the key issues we had to deal with in our work was especially that we cannot connect a subsonic state to a supersonic state in the usual way we solve a hyperbolic Riemann problem. Also, to understand better the evolution of the characteristic discontinuity that we experience in our work in a mixed type flow, and showing the appropriate compactness for the approximate boundaries, these free boundaries, so that we can get a global, well-defined solution. Okay, so this is a little bit about the steady Euler system. So in conservation form, we can write the 2D Euler system as the following. Here are four characteristic fields. The first and the fourth give rise to the shocks and rarefaction in the Riemann problems. The second and the third ones are the linearly degenerate field, which give rise to the vortex sheets or the entropy waves, the characteristic discontinuities in our work. This is how we connect states in the phase space along these curves. So the three main Riemann problems we had to solve involve the free boundary from the emerging from the convex corner, the interaction of weak waves with this free boundary, and the weak wave interaction. So the first two Riemann problems are the new ingredients of this work. The third one you can, for example, found in the earlier references I mentioned on the steady flows, especially with the vortex sheet analysis. So this is the free boundary Riemann problem. Here, the key point of this Riemann problem is to figure out where will this discontinuity emerge from the convex corner. So what we find is that we can figure out where it will go by looking at the slope. This slope is the ratio of the V component to the U component of the state U star, which is connected above to U plus by a 4 wave. And below this characteristic discontinuity, we have the still gas. So here, it's important. This is the strength of the 4th wave, and the slope is bounded by the state U plus and its difference from the background state. Here, K1 and K1 prime are positive quantities, and this bounded quantity M1 only depends on the background state and this epsilon, which is a small neighborhood of the background state. Because this is a small perturbation problem, it's important that we remain in this neighborhood to be able to solve all these nonlinear problems. Okay, so the next Riemann problem we had to find and solve for this work was the problem of the interaction of the first wave with the free boundary. Here, what happens is that the free boundary gets deflected, and there's a new 4 wave that is produced back in the domain. And here, the critical part is that this reflection coefficient, K2, is bounded. Furthermore, its size can be greater than 1, equal to 1, or less than 1, depending on what VL in the state vector UL is. So if it is less than 0, it's greater than 1, and if it's greater than 0, it's less than 1, and if it's 0, the coefficient is 1. And this coefficient is critical to find the right weights so that we can make the appropriate functional decrease, which I'll later talk about. So how do we construct our wavefront tracking approximation? So we have this approximation parameter delta. We take the initial data and make a piecewise constant approximation to it. So we solve the Riemann problems at the initial data x equals 0, and for y positive, and the free boundary Riemann problem at the convex corner. Then we approximate also any rarefaction waves, because the whole idea of wavefront tracking is we break up all the waves into piecewise constant jumps. Then we let the waves propagate forward, and we do nothing until 2 waves interact, or there's an interaction of the 1 family waves with the free boundary. Also, to keep the number of fronts in the solution finite, we introduce the notion of a generation, and we remove fronts with generation higher than n with the following criteria. So there are 3 important things we have to worry about at each time, because x is the flow direction, so x is also the pseudo time in this problem. So we have to worry about whether the total variation remains small. Also, we have to worry about whether there is an L infinity bound on the solution, so we can still stay in a small neighborhood of the background state. Also, the last thing we have to worry about is the number of fronts, whether they remain finite, in particular the reflections of the free boundary. Okay, so to control the total variation, we introduced the following Gleim functional. Here we represents the total strength of all the weak waves at a fixed time, x, and q represent all the waves that approach each other at this fixed time, x. Also, to weight the waves, we add additional weight on the first family waves. Here, this k plus is chosen to be much larger than this reflection coefficient I was talking about earlier. So the whole idea is to get control over total variation is to make sure this Gleim functional is monotonely decreasing across each interaction time. Okay, so there are 2 important cases we consider. So the first case is the usual case that comes from the Cauchy problem. I'm not going to say too much on that. The important case is this one, when the weak 1 wave interacts with the free boundary. Here, then we see that this choice of k plus becomes important when we take away this wave from the after the interaction happens in the Gleim functional. So what we are able to show is that for kappa and k plus independent of delta, and for any interaction time, that the Gleim function is monotonely decreasing, which implies that if the total variation is initially small, then the total variation will remain small for all times. This follows by induction argument using the Gleim functional. So this implies that the total variation of the solution will remain bounded for all times. Okay, so this bound on total variation gives us an L infinity bound on the solution. Furthermore, we can get an L infinity bound and the following bound on the free boundary. And here, again, these constants solely depend on the background state. Now, since we were working with the Euler system, it's not the strictly hyperbolic system where all these techniques of front tracking are designed for. So we have to deal with this issue of non-hyperbolicity and particularly this issue of generation, because we have waves coming back into the principal domain after their interaction. So what we note for this non-strictly hyperbolic issue is that the multiplicity of the eigenvalues are constant for states nearby. So as long as we are near this background state, we won't have this issue of crossing of the eigenvalues. Also, by assigning the 4 waves that go back into the domain the same generation as 1 family waves, we are able to extend the arguments from Holgen and Resborough's front tracking to our case to show that the number of interactions and reflections stay bounded for all times. Okay, to show the compactness of the free boundary and the solution, we know the following. So once we have the L infinity bound on the free boundary, we can extract a subsequence that converge uniformly on a compact set, and this sort of follows by an Arzelà-Scolite type argument. Here, furthermore, we can show that this free boundary is a Lipschitz continuous. Also, we have to use the following version of the compactness theorem to extract a limit solution. So here, the key thing we have to modify is for the free boundary, because to be able to apply it, we basically have to flatten out this component. And once we make this modification, we check all these conditions for this new function we define. So at this point, we get a limit solution. So of course, when we get a solution, limit solution, we have to check whether it is satisfies the appropriate entropy conditions. So here we go through the weak formalism and check all these equalities. Particularly, the first one comes from the conservation of mass, the second and third from the conservation of momentum, and the fourth one comes from the conservation of energy. The fifth one is the entropy inequality. So there's a difference here because there's a subsonic state below. There's an additional term in both of these quantities compared to, for example, the Cauchy problem. Okay, so furthermore, we have to check the following issues, because what happens is that once we introduce these approximations, we are taking away, for example, when we approximate the initial data by a step function, or approximate rarefaction waves by fronts, or remove fronts of higher generation, we are introducing errors. So we have to check how far our approximate solutions are from the actual weak solutions, and we have to do it over these approximate domains. The reason I say it's approximate domains because we don't know where the actual free boundary is. So we check that, and we do show that these errors do vanish as delta goes to 0. A critical part of that analysis is this lemma, which says that all the fronts of generation greater than n will be uniformly bounded by this constant c, which is independent of delta. Okay, so in summary, what do we accomplish? So using the wavefront tracking method, we construct an appropriate Glim functional that is monotonely decreasing in the flow direction using the key Riemann problems we solve, and we get global a priori bound on the total variation of each approximate solution. Applying a Haley compactness type theorem, we obtain a convergence subsequence to a global entropy solution in L1. So the theorem we prove is that if the perturbation from the background state is sufficiently small, then the initial free boundary value problem has a weak entropy solution that satisfies the following conditions. Okay, so at this point, of course, after existence, we are interested in uniqueness. But the problem here in trying to show uniqueness in a way you would do, for example, for a strictly hyperbolic problem, is that the two solutions could be defined in a different domain. For example, you could have that, for example, U would be, could be for a fixed X star, let's say, there could be some point Y star where U is in the supersonic region while the solution V is in the subsonic region. So the problem is that we cannot solve the Riemann problem to connect a subsonic state to a supersonic state along the Hoganeo curve in the phase space. So what we do is we introduce the Lagrange coordinate transformation so that the free boundary becomes a positive c-axis, and here the two solutions then become defined on the same domain. So, so we take a piecewise C1 weak solution and define the following transformation. These are the Euler-Lagrange transformation. Here, the point x0 and y0 is a fixed point on the transonic contact discontinuity, and here xy is a point in the domain. Moreover, we can choose any smooth curve, and this integration is along that smooth curve. Okay, here are some important properties of this transformation. First, it's well defined. Moreover, it's independent of the point we choose on the transonic discontinuity. Furthermore, it's Lipschitz continuous and one-to-one, provided U is positive or greater than 0, which is the case since we're dealing with the supersonic flow. So after applying this transformation, we obtain the following strictly hyperbolic system. Here, the energy of conservation becomes the Bernoulli law. So the transonic discontinuity becomes it becomes fixed positive c-axis in the Lagrange coordinate. Now we can formulate the following initial boundary value problem. Here, the important thing to note is that we still have this important pressure condition above and below the transonic discontinuity, which becomes a fixed boundary now. It's a fixed characteristic in the Euler-Lagrange coordinate. Now we can go back, once we can solve U, we can go back and obtain the free boundary in the following way. So this is the corresponding form of the initial boundary value problem in the Lagrange coordinate. Since the Lagrange coordinate is a continuous change of independent variable, we have that the both systems have the same wave curve, so we can solve all the Riemann problem, construct the Gleim function, and obtain a global weak solution to the following initial boundary value problem. So now to analyzing the L1 stability. So here the idea is to construct a Lyapunov functional and show that it's almost decreasing along pairs of delta approximate solution. Here again, delta controls all these errors. Now for fixed C and for each eta, we connect the state U eta and V eta by moving along Hogonian curves. And we donate by pi the strength of the ith Hogonian curve. So we also have to define these L1 weighted strengths depending on the wave interactions and the reflection estimates. And this is the form of the Lyapunov functional we use. Here, Q represents the wave interaction potential for wave 4. AI represents all the waves in U and V of the ith family. All the waves in U and V which approach the ith wave. And the key estimate we have to establish is the following, which can be broken down into further these two estimates. So this first one is similar to the Cauchy problem, so I focus on the estimate near the boundary. So here, this is different from the Cauchy problem, so we take two solutions near the boundary and denote by pi the strength of the ith shock in the Riemann problem. Now, the boundary condition we have is that the two flows must have the same pressure. So for the linearly degenerate case, the second family, we know that the eigenvalue is 0. Furthermore, since the eta axis is flat, its derivative is 0, so EB2 is clearly 0. Now to estimate EB1 and EB3, we note that if the two cases, if P1 vanishes, then P3 vanishes also by the boundary condition because of the fact that the pressure must remain same across the contact discontinuity, which is of the second family. In the second case, we look at when P1 is non-zero. This implies that P3 will not vanish. So in fact, there will be one compressive shock or leg shock or a three compressive shock or vice versa. So by choosing the weights C1 to be sufficiently large and provided that this quantity lambda 3 over lambda 1 is bounded, we can show that this expression is also less than or equal to 0. So we had the original free boundary value problem. We made a change of coordinates, and now we're in Euler, when we're in the Lagrange coordinate where this free boundary flattens out. Over there, we have shown both existence and stability of solution, the L1 stability of solution. So where does this put us in terms of uniqueness for our original free boundary value problem? So here we have to invoke the theorem due to Wagner, which says that for a system of conservation laws, we have that for any bounded measurable function of this system, if it satisfies the following properties in the sense of distribution, then this transformation is Lipschitz continuous, and this induces a one-to-one correspondence between the L infinity weak solutions of this system and the following system. So this is perfectly what we need to show uniqueness for our initial free boundary value in the Eulerian coordinate. Furthermore, these two corresponding solutions satisfy the respective entropy inequality, also as well as the Lex entropy inequality. So now getting back to the uniqueness for our original problem. So how do we do it? So we take two initial data to the initial free boundary value problem in the Euler coordinates, and let U1 and U2 and G1 and G2 be the corresponding weak entropy solution we obtain from the front tracking method. Now, we know that both U1 and U2 are bounded. So to show that U1 equal U2, we have to show that provided that the initial data are the same. So suppose V1 and V2 are solution to the initial boundary value problem in Lagrange coordinate that correspond to U1 and U2. Then by Wagner's theorem, we just need to show that V1 and V2 are equal. Now remember from an earlier relation, we can also show that G1 will equal to G2. So therefore, by uniqueness result in the Euler-Lagrangian coordinate, we just need to only prove the following lemma. Basically, we have to check that the corresponding initial data in the Lagrange coordinate respect the, each of the transformation, the Euler-Lagrange transformations we make based on U1 and U2. So in sum, what we show is that for initial data, U naught close to the reference state, U bar plus in this sense, so that the total variation is small. Then there is one and only one weak entropy solution to the initial free boundary value problem constructed by the front tracking method. If you reformulate this problem in the Lagrange coordinate as initial boundary value problem, we also have shown an L1 stability for that problem for any two solutions, V1 and V2 of the initial boundary value problem. Furthermore, this solution is unique in the class of viscosity solution in the Lagrangian coordinates. Okay, that's it.